Good morning all. My name is Mo Khan from HITEK Electronic Materials. Thank you for joining this technical webinar on thermal management materials. I would like to thank firstly the EDS Reconnect and the back office team for giving me this opportunity to do this technical presentation on thermal management materials. The aim and purpose of this thermal presentation is to provide the need and purpose of thermal interface material for an application, identifying the key characteristics of a thermal interface material to be taken into consideration when choosing a thermal interface material for an application, and also identifying the attributes to be taken into consideration when choosing a thermal interface material for an application. In a nutshell, it's demystifying thermal interface material selection for an application. I'll try to make this as informative. I'm pleased trying to get people up to the level playing field in terms of the knowledge about how to go about choosing a thermal interface material for an application. The content, the first segment will be a level playing field in terms of demystifying the concepts and terminology which suppliers and manufacturers try to use to confuse and create this issue of locking a customer. But today's presentation is trying to give that control back to you, the engineers, or to yourselves, to have that control back and trying to have that level playing field in terms of demystifying the terminologies and concepts associated with thermal interface materials. The next segment will be the kind of factors that affect thermal material selection, the list of other thermal management materials, and identifying two specific key characteristics of thermal interface materials in terms of young modulus and short hardness. So what are the advantages, disadvantages? Why do people talk about these characteristics? And hopefully I'll be discussing that in the presentation. The next segment, normally this next segment about materials would typically last me half an hour or this presentation, but I've chosen to use the material selector guide to identify certain materials I'll discuss throughout the presentation or in that segment. But please note, we supply the market leaders in terms of thermal interface materials from Parker Chimerics and Henkel Bergquist Materials as a one-stop shop for your thermal interface material selection. And also identifying a high-tech material in terms of super thermally conductive gap pad, which is 1416 Osmotic Kevin, which I'll be talking about that in that segment. The next segment will be about design considerations in terms of thin bond line, the roughness. What are these attributes and why have these to be taken into consideration? And also a case study as well about how to, if you have a tolerance stack or if you want to have one material, how do we go about using one material for an application, the different heights of components in electronics. And wrapping up things in terms of summary. Okay. When we talk about heat electronics, the heat is, for example, you have a microprocessor or an electronic device, which is drawing energy or power to perform a function or an action. So that if it's drawing and sucking all that energy, is creating a byproduct of heat, and that heat could create sort of reliability, efficiency issues of the component or the component performing its normal task. Efficiency, reliability, operating speed could be slowed down or shut down, or rebooting, or the blue screen of death, or worst case scenarios, the heat is so intense that it catches fire, but hopefully we don't have that. So you see on the top right hand corner, you'll see a microprocessor, greater surface area, the red being this high concentration of heat, normally concentrated in the center of the component. But please don't neglect the smaller components. As you can probably see, have smaller surface area and could be equally of concern and problematic when obviously managing heat. So when we talk about heat electronics, we associate that with thermal conductivity. In a nutshell, it's the ability of the material to transport heat away to an interface. An interface can be a core wall, a lid or a cover, or a heat sink assembled onto a component. Okay, there are 3 or 4 types of thermal management methods for dissipating heat. This presentation will concentrate on conduction using thermal interface materials being used with an interface, be it a cold wall, or which is a lid or a cover, or either a heat sink. Convection is using liquids or gases to transport heat away from a hotspot or a system that's generating heat. Radiation is a thermal radiation, which is in free space, bouncing from one substrate to the next and dissipating that way. We don't get involved in thermal radiation methods, but this presentation is to highlight they exist. Another form of dissipating heat is using, or we call it, some customers call it, or some within industry, advanced heat transfer technologies using heat pipes. With heat pipes, you could longer distances or longer length, you want to dissipate heat, or you have inside a computer, you will have a copper pipe assembled onto a heat generator component, be the microprocessor, and dissipating heat. But you still need a thermal interface material to assemble the heat pipe onto the heat generating component or system. Ideally, a strongly advised electrically isolated material. You want to avoid any shortcut. You want to achieve electrical isolation. So we provide thin electrically isolating thermal paste, which I'll be talking about later on in the materials segment. Okay, so we see a diagram with a microprocessor on a circuit board. Obviously, thermal radiation to free space, but you also could dissipate heat on the copper wires, on using with the solder paste onto the copper. But you need to have various methods of dissipating heat, not just on a heat sink on the top of the component, but it could also help to dissipate heat on the board. But if you are, please make sure that it's on pillars or somewhere or in connect into the core wall. So when we talk about heat, it is a form of electromagnetic interference. We do help, or HITEK do help with other electromagnetic interference like RF and magnetic, but this presentation will be concentrating on heat, how to manage heat and how to dissipate heat using a thermal interface material. So we'll be talking about conduction, and hence why the thermal interface will be used to provide better than air. Air is not good conductor of heat. Okay, so if you see a microprocessor, you have a heat sink assembled onto that. So what we're trying to do is be better than air. You might have nooks and crannies in terms of the heat sink, and that's where the thermal interface material is sandwiched between the heat sink and the component. So you see the orange part, that's the die, or that's where the component is, protected by a die and enclosed in its black kind of housing. So what we're trying to do is trying to get the heat from the heat drain component to the fins and out, and if you have a fan, it could obviously provide enhancements in the heat dissipating properties. Okay, so primary function of a thermal interface material, yes, obviously to be better than air, it's not good conductor of heat. Thermal gap pads or thermal paste, typically 1 to 5 watts per Kelvin. You can go up to 14, 16, which we'll be talking about in the materials section shortly. Obviously, aluminium, copper, you'll get good heat dissipating properties. Okay. In a nutshell, what we're trying to do with a thermal interface material is to manage the thermal resistance, to have the thermal resistance to be as low as possible, to penetrate the heat into the thermal interface material and let the interface be the core wall or the heat sink to do its work. Also, you have some machine finishes in the nooks and crannies, and that's what the thermal interface material is going to fill in those voids so you get good heat transfer. Other function of a thermal interface material could be electrical isolation. The gap pads could offer some shock and vibration, element dampening, cushioning, attachment of attaching a heat sink onto a heat generating component or a system. And obviously some of the materials can provide some outgassing, low outgassing if you're concerned about rework or silicon leach. Okay. So this might seem OTT in this slide, but these voids or these nooks and crannies can compromise or affect your thermal effectiveness to your interface, be it in the core wall or a heat sink. So it might seem OTT in terms of magnifying from 0.001 millimeter, but what we're trying to do with those nooks and crannies is to fill in those voids with a thermal interface material so that you could have effective heat transfer so that the interface could do its work. Okay, this list or this slide and the next, the list is not comprehensive, and some of these factors affecting material selection might not be relevant, or some might be. So The thermal path is identified. Is it going to be, what interface is it? Is it going to be a heat sink or cold wall, be it the lid or a cover or a heat spreader? What's going to help to dissipate the heat to the outside world? Tolerance tank, I probably think that's probably the key, probably one of the vital and challenges a mechanical design engineer or thermal stress engineers is probably the tolerance stack of third-party components, machine interface, and trying to have a one material or trying to have a material to handle the various tolerance stack. The gap between the heat sink or the cold wall is another factor, and also the how you're going to deflect the material via gap pad so that you don't put more stresses on the circuit board, the solder joints. You don't want it to rattle and vibrate if you use a high short hardness material. Some applications require thin bond lines. They understand that the thinner the material, let the interface do its work. We just want to fill in the nooks and crannies in terms of be better than them. Contact pressure to make sure it's evenly distributed. So obviously controlling the deflection. If you're using a gap pad, you want to avoid over deflecting and having compression set. So you want to be able to reuse that or be able to have it avoid it going to its compression set to build it for it not to recover its elastomeric properties. The thermal performance is probably a given, trying to get as high as possible, the movement of transfer. That's what's going to do all the hard work. It's not black art, it is there. You want to get a high value to get the heat to the interface. Electrical isolation, some of these typically, the higher thermal conductivity materials tend to have graphene or metal particles in it, and obviously compromise electrical isolation. So with the gap pads, you can use Kapton tape or thin Kapton to give electrical isolation. But boron nitride is probably typical fillers in the paste and gap pads. Assembly, dispensing, die cut, we do that on site, kiss cut. So if a customer sends us a drawing, we can provide that level of service in-house at HITEK. And either roll, preform, kiss cut made to your drawings, and with release liners so that you can stick it onto your substrates. Other things which could affect could be UR rating. Majority of materials are UR rating. Some applications require a gap pad in terms of acting like a cushion or dampening vibration movement, which is advisable if you are having those kind of challenges or those applications, and reworkable. Ease for removal, less residue. If it's a cure and place material in room temperature cure, it's quite challenging to remove it, or a phase change material, it could be challenging to remove it apart from the heat sink and a substrate. And our gassing typically could be for rework element of it, or if you've got lasers or lens, you want to avoid the silicon leaches, like a smear element of it. Okay, this list, there's a huge of materials out there that could offer heat dissipated properties, which HITEK can help. The thermal gap pads and thermal paste, thermal grease, this presentation will cover. Thermal epoxies tend to offer lower thermal conductivity, but structural bond, as in like not removable. We also do HITEK do thermally encapsulated potting materials, the StyCast range. The StyCast 2850 range. It could start from 1.25 watts per Kelvin right up to 2.26 watts per Kelvin thermal conductivity. So the StyCast encapsulates potting materials. HITEK do that, and we also do downpacking if required. Phase change materials could be in preforms, good bond line thickness, attachment. What happens is when the compound sandwich into a heat generating component and the heat sink, power it up your device. It heats up because of the components is heating up. It'll turn into liquid, pushes the air out, and attachment. So good wetting and thin bond line, but challenging to remove. So you would have to make sure that it heats up to 40 Celsius and with a sharp object to snap it apart. Thermal attached tapes, you could either have them die cut to the shape that you want, double-sided tape, but thermally conductive tapes. Thermoelectrically pads, very durable, punch resistant, could handle high torque within reason, and also provide thin bond line on thermal interface materials applications. Okay, if there was a slide to take away from today's session, this will be it. Okay, thermal conductivity, as I said earlier, you want it as high as possible. That's what's going to do all the hard work in terms of getting the heat off away from your component or your system to the interface. So you want to make sure the interface does its work in terms of dissipating the heat and moving the heat away, but you need the thermal interface material to move that heat from that hotspot to the interface. So it's a given, you want a high value. Okay, the next two characteristics. The thermal impedance, a thinner material will get the heat into it, but if it doesn't penetrate into it through and out, you're not going to get good thermal effectiveness. So what we try to say to customers, please have a low thermal impedance. The next thing to think about as a characteristic is the thermal resistance. Thermal resistance, you want it as low as possible, as in penetrating heat into the material through and out. The thermal academics struggle distinguishing between thermal impedance and thermal resistance. What we are saying today is try to keep them as low as possible and have the thermal conductivity at high value. So if you have two materials from different manufacturers, how do you go about choosing the right one or the best performance? Will be looking at lower thermal resistance, lower thermal impedance, and higher thermal conductivity. Okay, there are other key characteristics of some applications. Could be the shore hardness of the material, so you don't want to resolve any stresses. You might be able to exert any stresses. I mean, to me, 10% might be low and just sufficient, but some applications it could be too high and cause some problems in terms of some applications. The electrical strength, if you've got power supplies, so you want a voltage breakdown, we can provide that data in one of the data sheets. Outgassing. We can provide collected volatile condensable mass or total mass level percentages. So we could provide some outgassing data on the various materials that we represent. Okay, so why the focus on young modulus? So as I said earlier on, about a few seconds ago, about you want to put less stresses. You haven't got the ability to exert stresses, so you concern the solder joint, the element of exerting stresses could actually damage your component or a board. So young modulus materials tend to continuously change. They're not going to keep the static shape. So yes, you'll handle your stresses issues, but the longevity, liability in the field, that the material continuously oozes out or pumps out. But however, if you design features, surface roughness or cavity, you could be able to mitigate those risks. What we're trying to say is please start to have it not too high or medium to high, so it retains the shape. It can handle fatigue element of it, so you're not having that issue that why is my thermal resistance getting too high? It's because the material is oozing or pumping out and isn't attached to the substrates. In thermal paste, we call it the viscosity, an element of ability for it to pump out or to minimize the low pump out. Okay, shore hardness element of it. You want a softer material to handle the deflection forces, or you don't want to exert too much forces on it so that it affects the solder joint, similar to the young modulus material. But what we're trying to make you aware is that I'll put down 100 cycles. It could be actually more or less 100 cycles. What happens with a low shore hardness material in be it a typical hot generating component, in the middle a gap pad and a heat sink or cold wall or interface. You put that in a temperature cycling. I'll put down 100. It could be more or less than that. What happens is every time you temperature cycle it, its ability to you naturally don't get relaxation, but eventually it starts losing the thermal resistance becomes high, and as thermal resistance becomes high, then the thermal effectiveness gets compromised. But however, lower shore hardness material, good for vibration or dampening vibration as a cushion. Some customers use our gap pads, low shore hardness gap pads, as cushioning just to get any vibration or movement concerns, and obviously the enhancement of thermal heat dissipating properties in the material. High shore hardness material on static applications, yes, it's going to keep its shape. However, under vibration conditions, it'll go through the material and onto the solder joints or rattle the circuit board. So obviously you've got consent. So if you've got vibration movement, please try to avoid high shore hardness material. But please note that the high shore hardness material, you are going to, it's not going to be able to handle the thermal cycling. It will have a fatigue, thermal cycling fatigue in those kind of materials. Okay, so paste. Okay. The Berquist liquid paste are cure in place, room temperature cure, fills in nooks and crannies, so you haven't concerned about it flowing out. Depending on what the material it is, it could actually stay in place, and a cure in place will have good bond. It's not a permanent bond, but it'll stick into the substrates. Save money in terms of with the gap pad, you paying for the waste. With the paste material, you could achieve a thin bond line. A thin bond line could be from 2mm up to 2.36 millimeter. Otherwise, it'll dribble and droop like a mushroom kind of elemental. But these materials could be used in automated process or inline process. Tend to be with a static nozzle to mix it, but room temperature storage, so it doesn't need any refrigeration element on it. So the Berquist materials tend to be typically the ones in red, the TG, the thermal gap filler 3600 is probably the widely used one, and the next one is probably the TG 1500. These are the most typically used within the Berquist two-part liquid gap fillers. But typically these will have twin pack cartridges with a static nozzle. Please, if you're doing a job lot, you probably could use the static nozzle. But if you are going to stop and continue the next day, please, you'll have to remove that static nozzle, put the end cap in, or purge the system before reusing it. Whereas the Chemerix range are single part materials, easy dispensable, minimize pump out, as in no curing required, but reworkable, as in like it's not going to stick. They have got tackiness, but they're not going to stick, as in like bond. Typically, the thermocop, the TC50 5 watts per Kelvin, the gel 30 is probably where I would normally typically start. The 3.5 watts per Kelvin is the paste that I typically would start with. For the heat pipes, I would try to suggest a gel 8010, 3 watts per Kelvin because of thin bond line. That's green principle. Also got a gel 25 non-silicon version as well. But as this end is obviously tends to be easy to work with, flows better. The higher the thermal conductivity, obviously the gritty. But there is a new material which is gel 75, 7.5 watts per Kelvin, which recently come into the market. So that's the 7.5 watts per Kelvin. Okay, within the Berquist range, in terms of various gap pads, the sill pads, electrically isolated materials, which are sill pad, very durable materials, punch resistant within reason, could handle high torque. Typically, in terms of the gap pads with the 5-class base, is normally the thermal gap pad 3000 or HC 5000, the 3 watts per Kelvin or the 5 watts per Kelvin are typically quite the industry proven pedigree and used on a variety of applications, and we hold stock on various of these materials as well. So in terms of new development, the ultra low modulus materials, the thermal gap pad 12,000 ultra low modulus. There's also a 10 watts per Kelvin, which are relatively new. And obviously within the Berquist range, we've also got silicon free if you've got Agassian challenges. Okay, within the Chemerix range, in terms of the gap pad materials, the 579, 3 watts per Kelvin, shore hardness about 30. This is the material that I would typically start with. Got good proven pedigree traction, used on a variety of applications. These materials could come from 0.25 millimeter thickness right up to 5 millimeter thickness materials. And come with other GE, which is a glass fiber mesh to avoid any separation, and also helps to keep the material to avoid any oozing or pump out. The aluminium is also used as a sort of like a give it some rigidity, and also to have the pressure sensitive adhesive. So if you want a pressure sensitive adhesive gap pad, you'll start putting an A in front of the part number. But as you see from this segment here, the higher shore hardness, the higher thermal conductivity, 6.5 within the. But within the Chimerix range, they do have a pad 60 and a pad 30, which are relatively new materials, which is pad 60 6 Watt Kevin, and a pad 30 supposed to be 3 Watt Kevin, it's actually 3.2 Watt Kevin. Okay, so as you can see from the Chimerix range, within the Berquist range, we can help with the thermal thin pads, the gap pads, and the phase change material. Phase change materials, as I said earlier on, when it heats up, it turns from a ceramic to liquid and pushes the air out, so you've got good bond line thickness and attachment as well. And obviously greases for smears. I'm not a big fan of greases because if it heats up, it could spread, but they're good, better than air. In terms of Chimerix range, as you can see from the gap pads we talked about early on, right up to 3.5 or even 6 Watt Kevin, which is a relatively new material, which is hence why it's not into this selector guide. Phase change materials similar to the Berquist materials, the thermal attached tape, double-sided tapes, the potting, cure in place materials, and heat spreaders, and obviously the grease. Okay, this is our super thermally conductive gap pad, which is a HITEK product, made of graphene and carbon fiber strands. Yes, it's not electrically isolating, but you can put thin Kapton sheets to get the electrical isolation, which you might have a loss, but you're still starting with a high value of thermal conductivity, so you see some loss in it. Typically 14 or 16 Watt Kevin are the highest values of gap pads which you do, and if you achieve between 15 to 20% deflection, you should get those values. We can provide test data, different types of thickness available up to 200 Celsius, and different sheet sizes available as well, 0.50 to 2 millimeter thickness available. There's some excellent thickness on these materials. So we can provide test data if you need to prove that different types of compression force, deflection forces are applied, and can provide data. Okay, in terms of bottom line, sorry, I've got 9 minutes left to do this. The phase change materials, able film, you could actually achieve a 7 Watt Kevin. So you probably, it's how much like a phase change material, you have to apply heat in an oven for it to become a liquid. Ceramic part becomes a liquid and pushes the air out and attachment, but you won't be able to remove it. Thermal attached tapes, thermally conductive tapes, the core thermal materials, as electrically insulating pads, thermal grease you can, and the gel 8010, obviously with a small particle size you can achieve a thin bond line. Surface roughness, please, it's good for better, good aids in the thermal resistance to penetrate heat into the material and throughout. So please, I would always advise, please have some roughness but if you've got a thin bond line, please, thicker materials handle tolerance is better and fills those nooks and crannies, but not thinner. Okay, so when we talk a thin bond line, typically the crossing polymer system, if you break that crossing polymer, say typically the rule of thumb is 3 times the particle size of the filler of the paste. Anything less than that, 2 or 1, you break the crossing polymer and you have compression, particle separation. If you are going to use a thermal paste, please think about using a tapered tip for the smooth flow dispensing. Okay, so what does this slide say? So what it's trying to indicate is that air is not good. You could trap air in it. So the serpentine and spiral would minimize any air trapped inside when you're using a thermal paste. So these are either done on XYZ robot. So please, what we're trying to say is that you are going to get greater surface area contact, but you want to minimize any air trapped in when you're using the paste. Okay, so as you see for 3 diagrams here, the metalwork, the interface using the thermal paste, instead of dedicated heat sinks, you're using an interface or lid as a heat sink. The middle segment is trying to show you interchangeable in terms of there used to be a gap pad, but now it's dispensed in. You can actually have one whole piece rather than 2 whole pieces or 4 separate pieces for minimize any touch time. But the XYZ robot will dispense it, and obviously to the shape that you want and the location. The last segment is a case study in terms of they tried to use one material to handle the different heights of components and tolerance stack. So they machined as a PXA unit, they machined a galley of pockets using a gel 30, 3.5 was the carbon material dispensed in those pockets, so that you could have one material to handle the different heights of components, so minimizing the inventory of holding the various thicknesses. Okay, to wrap up, I've got 6 minutes left. If I was to summarize, the challenging will be the tolerance stack. It's trying to have one material to be able to handle the tolerance. It's advisable to use a thinner material to let the interface do the hard work. Thicker materials handle tolerances better. But please, within our industry, it's the deflection. If you stay within the deflection range, we minimize compression set and being able to make sure you get thermal effectiveness of that material. And hence why making sure that clamping force is evenly applied in distributed pressure. The mating surfaces, please, I advise customers, please have some roughness, better than nothing. It just aids the contact resistance penetrate into the material through and out. In terms of thermal resistance, probably more important for thermal paste and gels, and obviously thermal conductivity in the gap pads. Okay, any questions? I've got 6 minutes. Okay, I have a case study. A customer said that, when I attempt to cycle my using a gap pad, why is my thermal resistance going up? So basically, my thermal effectiveness is being compromised. So what I try to say to them is when they do a sort of like a -20 cycle up to 80 plus 80. So when they finish the cold cycle, is to take the unit out and whatever the torque setting is and retorque it, and then continue the temperature cycling. So please, these materials will contract inwards and outwards, are temperature sensitive in terms of temperature cycling. So please, you want to minimize the gap, not over torque it, so you have compression set and you've obviously not going to get good heat transfer. If there's any other questions, as I've got 5 minutes. Okay, I would always try to advise a thinner material. If some customer says, "Mo, can I deflect it? I've got tolerance stack. I need to be deflecting the material about 50–60%." I said, just use a smaller, thinner material so that you could mitigate those high exert forces or to handle those tolerances. Another thing to consider is that with the paste, I normally say 2 millimeter thickness. You could go up to 2.36, but if you have a galley pocket, you could go up to 5 if you really have to. Okay, 5 minutes. There's no questions in the chat. Thank you all. No other questions from the audience. Thank you so much. Please see HITEK as a one-stop shop for your thermal interface materials. We die cut on site, either with a die cut tool or laser cut. So today we talked about thermal interface materials. We can help in terms of protecting your electronics, in terms of electromagnetic interference using EMC gasket materials, or magnetic interference using radar absorbed materials. So please see HITEK as a one-stop shop in terms of solving your challenges in terms of protecting your electronics. And thank you so much for giving me the opportunity for doing this technical webinar. And thank you, EDS Reconnect, for giving me this opportunity and the back office. Thank you. Thank you all.